So the last section we're going to discuss is going to be on damped oscillations. And this is what we typically encounter in real life. And you guys probably noticed this in lab. When you pulled the mass on the spring down, it never actually went back to its original position because there were non-conservative forces working on the spring. So the one we're going to focus mostly on is going to be underdamping, and that is what we would have seen in lab. Alright, so we learned earlier that when a mass moves through a fluid, the frictional force is going to be proportional to the velocity. So we're going to sum our forces on our mass once again, but this time we're going to take into account the fact that not only do we have the spring force, but we have this frictional force acting on the oscillator. And this is what we're going to call our dampening constant. Alright, so we're going to rewrite all of these in terms of x. So acceleration is the second derivative of our position function. This is already in terms of our position function. And the velocity is the first derivative of the position function. Now I can't actually show you guys the next step because this involves a differential equation, but when we solve this differential equation, we would get this relationship here. Now the important thing to focus in on with this relationship is this term here. This is going to cause exponential decay so that when the oscillator oscillates over time, your amplitude gets smaller and smaller because you're going to be multiplied by e to the negative something that keeps getting bigger. So you're going to see your amplitude decrease over time. We also have a different frequency here, or angular frequency, and it still relates to our spring constant in the mass, but it also takes into account the idea that you do have a dampening constant to worry about. So this is underdamping. Underdamping here is going to occur when you get an oscillation with a steadily decreasing amplitude. And this is going to happen when your dampening constant is less than 2 times the square root of k times m. Our other two options are slightly more extreme. We have critical dampening, and this occurs when our dampening constant is equal to 2 times our spring constant times the mass. There is no oscillation, and so you pull it back, let it go, and it just goes to equilibrium. The same thing occurs with overdampening. So this occurs when you have your dampening constant greater than 2 times k times m. And once again, there is no oscillation, but the return to equilibrium is slower. So the big takeaway here is the idea that in real life you're going to see non-conservative forces at work, so that you get dampening, so you never actually return to that original amplitude. And it may decay slowly over time, or you may get more extreme examples where you're in more viscous fluids where it may not oscillate at all and it just returns back to equilibrium position.